Hello, my name is Antti Roolila. This is climate lesson number 3, composition of the atmosphere. The composition of the atmosphere should be pretty clear, and if you look at these figures, it looks like that we know very well what is the composition, but in the end, you will find that this is one of those critical issues, how we can handle the composition and get totally different results. The gases with black font, nitrogen, oxygen, and so on, are those gases which are not greenhouse gases. These molecules have one or two atoms, and it means that they cannot absorb radiation. The gases with red font are greenhouse gases. Carbon dioxide, 385 ppm. ppm means part per million. And then we have methane, 1.8 ppm. Nitrous oxide, also called nitrogen dioxide or nitrogen oxidule. And ozone, very small amount. And then it says in the same presentation that water vapor concentration is about 0.4% over full atmosphere, varying from 1 to 4% at the surface. This is not totally true. Atmosphere, it says here, but it should read troposphere, then it's about correct. Let's see why there is not a single figure for water concentration in the atmosphere. The reason is here. The water concentration in the atmosphere varies a lot according to the altitude. And you may think that here above 10 kilometers it's 0, but the scale is just cheating a little bit. It's not 0. But for carbon dioxide, the concentration is almost stable up to 80 kilometers. And you may think that this has a strong effect on greenhouse calculation, but it turns out that it's not so. We will come to this point later on. Then we have ozone, which is very special gas having many roles in the atmosphere. In the troposphere, the concentration is very low, but it's about 100 times bigger in the stratosphere, above 10 kilometers up to 50 kilometers. And the scales of these figures are not the same. And it means that this water concentration here in the stratosphere is in fact is the same as ozone concentration in the stratosphere. Methane and nitrous oxide concentrations are pretty much stable in the troposphere. The water concentration varies a lot according to the altitude in the atmosphere, but it varies also according to the different zones which can be found on the Earth. I have here 3 zones. Tropical zone, which covers about 40% of the area of the Earth. Mid-latitude zones covering 45%, and polar zones covering about 15%. And if we are looking at these profiles, we can see that the highest amount of water can be found in the warmest place, it means at the tropical zone, and the lowest values are, of course, in the polar zone at winter time. Here I have calculated the average profile of the Earth based on these values, using these percentage values, and this is the result. And as you can see, I have used just a single figure to indicate how much water there is in the atmosphere. And that figure is called prcm, precipitated water in centimeters. It means that we think that we condense all the water which is in vapor form in the atmosphere. And in this way, the result is in centimeters. And it's really so that if we take the whole atmosphere, the amount of water calculated as liquid is only in centimeters. This figure, which is here 2.69, can be found also in worldwide data banks. Here are two names, and they both give the same concentration or same amount, 2.6 centimeters water in centimeters. And it means that if you are looking at different calculations, you should find out what is the water concentration. It's very simple figure, 2.6 centimeters, or if you like, in inches, about 1 inch. That's a good measure how much water there is in the atmosphere in average. Here is the same thing as shown earlier, but now I have a graphical presentation copied from the net page. The data is taken from the third data bank, and it shows in the same way that the average concentrations of the water is pretty steadily about 2.6 centimeters. The time scale here is from 1983 till 2010. So we have all the reason to believe that in average the water content in the atmosphere is 2.6 centimeters. This slide is a little bit too early because it is based on the absorption calculations. This graph I have not seen anywhere. It has been taken from the two papers written by Ohmura and by myself. And here is the total absorption as a function of the altitude from 0 level up to 11 kilometers. And we can see how quick is this absorption. At 10 meters, 34% is already absorbed. At 100 meters, 67%. At 1 kilometers, 89%. And up till 2 kilometers, 95% has been absorbed. At 11%, 98%. So only 2% is left above the 11 kilometers. And this is one good reason why the greenhouse effect calculations can be calculated in the troposphere below 11 kilometers altitude. So it turned out that 95% of absorption has taken place before 2 kilometers altitude. That's why I prepared this table showing how much there is water below 2 kilometers altitude. The average percentage is 1.22%. This 1.22% means that below 2 kilometers altitude, water vapor, water molecule, is the thirdly most common molecule in the atmosphere. In many places in Wikipedia, it says that water vapor is some kind of trace gas, but actually it's not. It's the third common molecule below 2 kilometers altitude. It's very difficult to compare the volumes of greenhouse gases. What is the difference between percentages and ppms? That's why I prepared these cubes. This is the situation below 2 kilometers altitude, and this picture shows how much there are different greenhouse gases in 1 cubic meter. The biggest cube is water, and the second biggest is carbon dioxide. The volume difference between these two gases is same as 30 to 1. There are 30 times more water molecules. Then we have those smaller greenhouse gases, methane, very small cube, nitrogen oxidule, even smaller, and this very, very tiny pin here, red pin, that's the concentration and volume of ozone in the troposphere. I have two other cubes here. This red one is the volume of ozone in the stratosphere, and this blue cube is the volume of water in the stratosphere. They are about the same size. This matchbox is here just to show what are the measures. So they are the actual volumes, how much there is each greenhouse gas in 1 cubic meter below 2 kilometers altitude. Here are the 4 layers of the atmosphere. The troposphere's temperature profile starts from 15 degrees and it's going till minus 55 degrees. Thereafter, the temperature rises again, and it's caused by greenhouse gases, ozone, water vapor, and carbon dioxide. They absorb ultraviolet radiation, and temperature is coming back to something minus 10 degrees. Then it's going down again till minus 90 degrees about in mesosphere, and thereafter it starts to increase again in the thermosphere. This is the last slide of this presentation. It's an amazing photo from the space, taken from a space shuttle. This space shuttle here is Endeavour, and the background colors are something special. We can clearly see the different layers of the atmosphere. The lowest layer is troposphere, brownish orange color. And how sharp is this borderline? It's tropopause, and above this is stratosphere, white color. And above the stratosphere is mesosphere, blue color. And so when you see blue sky, you are looking at mesosphere.